Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial System Engineering. This lecture is on ARMA modeling. And in this lesson, I will introduce one of the most useful time series model, ARMA model, which is at the basis of all the models introduced in this course. In this lesson, I will focus on basic concepts of this model. Let's recall the definition of a time series. A time series is a sequence or collection of random variables with some similarity in terms of the probability distribution, also called a stochastic process. For a time series, the sequence of random variables, or the stochastic process, is indexed by time. We commonly refer to a time series as both the stochastic process from which we observe and the realizations or observations from the stochastic process. It's important to highlight that the time series data we commonly observe in practice are realizations of stochastic processes and thus come with uncertainty. At the core of modeling time series is the concept of stationarity. Stationarity means that the probability distribution of a time series does not change when shifted in time. Formally, it's defined by three conditions. First, we assume that the variance is constant and finite. Second, the mean is constant over all time points. Third, the covariance of the time series at any two different time points R and S is the same as the covariance of the time series at the shifted time series by any time t. The model introduced in this lecture is the ARMA model, which stands for auto-regressive and moving average, and is defined formally as follows. A time series is an ARMA process if it is stationary and for every t, or at time t, it is modeled as on a slide. It consists of two parts. The first part is the so-called AR or auto-regressive part of the model. The auto-regressive part models the relationship between xt and past or lagged observations, lagged variables xt minus 1, xt minus 2 up to xt minus p. For example, if we observe a high GDP this quarter, we would expect that the GDP in the next few quarters are high as well. In this AR formulation, P is called the autoregressive order of the model. This first part is an intuitive way to model a time series based on past data. The second part of the model is the so-called MA or moving average part of the model. Using the MA, we can model that the time series at time t is not only affected by the shock at time t, but also the shocks that have taken place before time t. For example, if we observe a negative shock to the economy, say a catastrophic earthquake or a storm like we had in the past few weeks, then we would expect that this negative effect affects the economy not only for the time it takes place, but also for the near future. The moving average is a linear combination of white noise. In this formulation, Q is called the moving average order of the model. An ARMA model can include both or just one of the two components. It can simply be an AR process or an MA process. Practically, if the AR order P is 0, then we only have an MA process. Reversely, if the MA order is 0, then we only have an AR process. Last, the ARMA model defined on this slide is for a process or a time series with mean 0. If the mean is mu, then practically xt minus mu is an ARMA process as defined on the slide. Let's establish important notation used throughout this lecture. We often write the ARMA model in a more compact form as provided on the slide. That is, we multiply xt with phi of the operator b, representing the left portion of the model equation, and multiply zt with the theta of the operator b, representing the right portion of the model equation. The functions phi and theta are defined further as on the slide. Phi is a polynomial of order p with coefficients given by the AR portion of the model. Theta is a polynomial of order q with coefficients given by the MA portion of the model. The polynomials are called the auto-regressive and moving average polynomials. The operator b is a lag operator. When applied to xt, we move the index back one time unit, giving xt minus 1. When applied multiple times to xt, for example k times, we move the index back k units, given xt minus k. ARMA models are at the core of modeling time series for a series of reasons. First, recall that we defined the autocovariance function for a stationary process depending only on the shifting age lag. We'll continue to use this definition for an ARMA process. The condition here that the covariance function decreases as we decrease the lag age means that the dependence in a time series becomes smaller and smaller as we increase the lag between two time points of the time series. If this condition holds, then it is possible to find an ARMA process with the same autocovariance function. That is, there exists an ARMA process for any autocovariance function with this property. A second important property of an ARMA process is that the linear structure of ARMA models makes prediction easy to carry out. In summary, in this lesson, I introduce the basic concept of ARMA modeling. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This last lecture is ARMA modeling. And in this lesson, I will illustrate ARMA models and estimated covariance function using a simulation study. Let's begin with the simplest ARMA process, the white noise process, which consists of a sequence of uncorrelated random variables with equal mean and equal variance. Note that the distribution of the random variables does not need to be normal. In fact, I simulated here in this example white noise when the random variables have a normal distribution and an exponential distribution. In this R code, W is a vector of randomly sampled normally distributed variables with mean 0 and variance 1 of length 1000, and W2 is a vector of randomly sampled exponentially distributed variables with rate 1 of length 1000. I rescaled both vectors for comparison. I also converted the vectors W1 and W2 into time series using the TSR command. Last, I plotted a time series W and W2 along with the plot of the sample autocorrelation functions. Here are the plots. The upper plots are the time series for normal on the left and exponential on the right. We do see a difference in how the observations of the two time series vary over time. For normal distribution, they vary around 0 quite symmetrically, while for exponential, all values are positive, lacking symmetry. These are the characteristics of the two distributions. More generally, however, the patterns are very choppy and patternless. The bottom plots are the sample autocorrelation functions. An autocorrelation function plot is a bar plot where each bar corresponds to one lag age starting from 0 to a maximum lag. The height of each bar corresponds to the value of the sample autocorrelation for the corresponding lag. We can also provide similar plots for the autocovariance function, for the sample autocovariance function, where the bars will be the values of our autocovariance function. As highlighted in these two plots, we see that the sample autocorrelation is large for lag equal to 0. In fact, it's equal to 1. This means that for these processes, the sample autocovariance is small, approximately 0 for all lags, except for the 0 lag. This aligns with the property of the autocovariance function of a white noise, which is non-zero, it lacks 0 and is equal to the variance, but is 0 otherwise. This ACF plot for the two simulated processes in this example will be seen for all white processes regardless of the data generation process. In fact, we'll use these characteristics to evaluate whether the process is a white noise or not, as we'll see in many examples in this course. In the next simulation, I simulated again white noise from a normal and an exponential distribution, but this time the white noise will be filtered to obtain a moving average process. The two processes we'll simulate are shown on the box in the right. The first process has coefficients minus 0.5 and 0.2, whereas for the second process, I changed the first coefficient from minus 0.5 to 0.5 to see how this change will be reflected in the autocorrelation function. Next, I use the filter command in R to generate a moving average process given the white noise process. The input in the function consists of the white noise and the vector of coefficients specified in filter equal to A and side equal to 1, which means that we're generating an MA process. Last, I will only consider the process starting with 3 since the first two values are lost, because we need to generate x3 given as z1 and z2, but there is no past white noise series to generate x1 and x2. We apply this procedure to both sets of coefficients and for normal and exponential distributions. The ACF plots are here. The upper plots are for the normal and the bottom are for the exponential distribution. Across all ACF plots, we see one important common characteristics. All of them have the first two values of the ACF large outside of the confidence band, whereas for other lags, the sample autocorrelation is small, close to 0. We'll see that this is a characteristic of an MA process. Last, there is a difference between the ACF plots for the two different sets of coefficients. The sample ACF is positive for lag equal to 1 for the processes with coefficients 0.5 and 0.2, versus it is negative, a lag equal to 1, for the processes with coefficients minus 0.5 and 0.2. From these examples and other examples, we see that although xt is modeled as a moving average model, thus a linear combination of white noise, then xt and xt minus 1 are still dependent on the sample sequence of white noise. Thus, they are correlated. This correlation is reflected in the ACF plots. In this example, we'll take a closer look at an MA process with a non-stationary noise ZT. We begin by generating the white noise, then we filter a white noise that it is not stationary. Specifically, the MA process has coefficients minus 0.2, 0.8, and 1.2. But the noise is a white noise multiplied by 2 times t plus 0.5. Thus, the noise is non-stationary. The time series plot for this simulated MA process is here. From this plot, we see clearly that there is no stationarity in the process. Its distribution changes as time shifts. We also note a large variability at the later time points compared to the earlier time points. The ACF plot is provided here. The ACF plot does not indicate, however, non-stationarity. In fact, we see that the sample ACF is large for lags 0, 1, 2, and 3, but not for higher lags, which is an indication of an MA process. Thus, the sample ACF plot indicates an MA process of order 3, even though the noise ZT is non-stationary. This may not be the case for other processes with non-stationary noise. Last, let's take a closer look at AR processes. Here I simulated AR processes with lags 1 and 2. To do so, I simulated a white noise first, then applied filter R command with the coefficients specified by filter equal to A2 or A1, and method recursive to specify that we simulate an error process instead of an MA process. The coefficients of the first process are 0.8 and 0.2, whereas for the second process, the coefficient is 0.5. The AR2 process is non-stationary, whereas the AR1 process is stationary. Here are the time series plots for the AR2 and AR1 along with their ACF plots. The time series of the non-stationary AR2 process shows clear non-stationarity since the distribution of the process changes as time shifts. The ACF plot of the non-stationary process also indicates non-stationarity. When the ACF values decrease slowly as for this AR2 process, this is an indication of non-stationarity. On the other hand, for the AR1 process, the sample ACF is large for lag 0, 1, 2, and 3 only. Note that we cannot use the ACF plot to identify the lag of the AR process as we did for the MA process. We'll get back to this aspect in a different lesson in this lecture. In summary, in this lesson, I introduced ARMA models and the estimated autocovariance function using a simulation study.